Studies Section 8. Probability and Random Variables. Introduction. Due to the peculiar nature of man, social science phenomena are basically characterized by uncertainty. A social science researcher does not have the absolute degree of freedom in predicting social phenomena, although the uncertainty principles create a kind of complexity in making inferences in social science. There is a need to develop a tool that will enable us make inferences. Probability is the tool that enables inference making even at the face of uncertainty. In this lecture, we shall examine the basic principles of probability and random variables as it relates to social events. Objective. At the end of this lecture, you should be able to 1. Understand the use of probability in making predictions. 2. Link set theory, event, and outcomes in interpreting probability statement. 3. Compute the probability of a given event. Pretext. Answer the following questions before you read the lecture note further. 1. If the probability that an incumbent governor will win an upcoming election is 3/5, what is the probability that he will lose the election? A. 3/5, B. 4/5, C. 1/5, D. 2/5. 2. The collection of all possible outcomes in an experiment is called A. Sample size, B. Sample mean, C. Sample space, D. Sample half. 3. The outcome of an experiment is called A. Science, B. Event, C. Sample space, D. None of the above. 4. A function that associates a real number to every element event in the sample space is called A. A random variable, B. A dependable variable, C. An independent variable, D. None of the above. 5. The probability of any given event can only have values that lie between A. -1 and +1, B. 0 and +10, C. 0 and +2, D. 0 and +1. Content. Section 1. Elementary Probability Theory. As we have mentioned in the introductory section of this lecture, virtually all human activities are uncertain events. For instance, a candidate in a presidential election will think of the possibility of success or failure. In an election, a candidate will either win or lose. Our task here is to predict the chances of winning or losing the election. By simple definition, the probability of an event E is given by probability of E is equal to total number of occurrence of event E over total sample space. Equation 8.1. So, how do we define an event, an outcome, and a sample space? Event and outcomes. In statistical terms, an event is an outcome of an experiment. Thus, success is an event in an election, so also failure is an event. In fact, the expected outcome of any election is the set A equal to win, lose. Likewise, in a war game, the expected outcome of a war is the set B, win, lose. Thus, in the war experiment, win is an event and lose is another event. There are some experiments that have more than 2 possible outcomes. The collection of all possible outcomes in an experiment is called the sample space. Thus, in numerical terms, the sample space of an election is 2, that is, win or lose. Likewise, The sample space of a war game is 2 by using our definition for probability of an event E, equation 6.1. If E is the event that a candidate wins in an election, then probability of E is equal to half. Here we assume that the game is fair. We also assume the two events have equal chance of occurrence. Since there is only one favorable way that win can occur and the total sample space is 2, let us illustrate the concept of probability with another example. Example 6.1. A Senate Committee on Education consists of 5 AD senators, 7 ANPP senators, and 8 PDP senators. What is the probability that a senator selected at random from the committee is a PDP senator? Solution: total sample space is equal to 5 plus 7 plus 8 senators is equal to 20 senators. Number of outcomes favorable to PDP senators is equal to 8. Let E is equal to event of selecting a PDP senator. Then, using equation 6.1, probability of E is equal to 8 over 20 is equal to 0.4. This is a fairly high probability. 2. Complementary events. Two events are said to be complementary if they both exhaust all possible outcomes. For instance, if the event of winning a war is half, and the event of losing the war is also half, then the event winning the war plus not winning the war is equal to half plus half is equal to 1, which exhausts all possible outcomes in that experiment. We also assume a fair game here. As a rule, if A complement is the complement of event A, then probability of A complement is equal to 1 minus probability of A, equation 8.2. 3. Mutually exclusive events. Two events are said to be mutually exclusive if the occurrence of one prevents the occurrence of the other. That is, the two events cannot occur at the same time. For example, in a single election, the event W is equal to candidate A wins and L is equal to candidate A loses are mutually exclusive events. A candidate cannot win and lose in a single election altogether. Thus, P W union L bracket is equal to probability of W plus probability of L, equation 8.3. Number 4. Independent event. Two events are said to be independent if both can occur together at the same time. That is, the occurrence of the one does not prevent the occurrence of the other. E.g., let us define two events as follows. A is equal to Nigeria wins the Bakassi War. B is equal to Nigeria wins the next African Nations Cup. Then A and B are said to be independent events since both events can occur at the same time. Therefore, probability of A intersection B is equal to probability of A times probability of B, equation 8.4. We call equation 8.3 the addition rule of probability, and we call equation 8.4 the multiplication rule of probability. If W and L are not mutually exclusive, then equation 8.3 becomes probability of W union L bracket is equal to probability of W plus probability of L minus probability of W intersection L bracket, equation 8.5. Example 8.1. Suppose it is known that the probability of winning the Bakassi War is 0.58 and the probability of playing at the finals of the next African Nations Cup is 0.61. What is the probability of winning the war and playing at the finals? Solution. Since the two events are independent, we shall use equation 8.4. Let A is equal to event of winning the war. Therefore, probability of A is equal to 0.5A. Let B is equal to event of playing at the finals. Therefore, probability of B is equal to 0.61. Then, probability of A intersection B is equal to probability of A times probability of B is equal to 0.58 in bracket, 0.61 in bracket is equal to 0.35, which is a weak probability. Section 2. Random variables. By simple definition, a random variable x is a function that associates a real number to every element event in the sample space. Let us illustrate this concept by the war game. In a single war game, the sample space is success or failure, S, F in bracket. Now, let us assume that success has a numerical value 1 and failure has a numerical value 0. That is, sample space S, F in bracket, X implies values 1, 0. The linkage between the sample space and the values, figure 8.1, is provided by the random variable x. Thus, the function that a random variable x performs is to associate a real number 0, 1, 2 to every element of a sample space. Discrete and continuous random variable. A random variable that takes only a countable number of values such as 1, 2, 3. N is called a discrete random variable, while a continuous random variable is that which can take any one of the infinite number of values in a line interval. Section 3. Probability distribution of a discrete random variable. In the preceding section, we examined how a random variable x maps the sample outcomes to the set of real numbers in order to make an inference on the larger population. However, we need to know the probability of occurrence of the values of the random variable x. This probability, when expressed in the relative frequency form, is known as the probability distribution of x. Probability distribution can be expressed in the following ways: in tables, graphically, using the histogram, in mathematical notations. Illustration: since the game of tossing a coin is fairly similar to the game of war, at least with respect to the dichotomy head or tail and win or lose, all other variables held constant, we shall use a coin tossing example to illustrate our discussion in this section. Example 8.2. Determine the probability distribution of an experiment consisting of independent toss of two fair coins. Solution. Let us define a random variable x as the number of heads observed in the experiment, that is, head, tail, success, failure. Diagrammatically, figure 8.3, outcome x, tail, tail, approaches values 0. Tail head approaches 0. Head tail approaches 1. Head head approaches 2. Probability of x approaches 1 over 4 approaches 1 over 2. If the first coin and the second coin result in tail TT, we record value 0, which means failure. If one coin results in H and the other in T, we record a value of 1 to show that only one success occurred. Finally, if both coins result in head HH, we record 2 to show 2 successes. However, the probability associated with each value of x, denoted by probability of x, is calculated as follows. Let A1 is equal to first coin is head. Probability of A1 is equal to half. A1 prime is equal to first coin is tail. Probability of A1 prime is equal to half. A2 is equal to second coin is head. Probability of A2 is equal to half. A2 prime is equal to second coin is tail. Probability of A2 prime is equal to half. Probability of TT is equal to probability of getting 2 tails, is equal to probability of first coin is tail and second coin is tail, is equal to probability of A1 prime intersection A2 prime is equal to probability of A1 prime times probability of A2 prime is equal to half times half is equal to 1 over 4 independent events. Probability of HT or TH is equal to probability of getting one head is equal to probability of first is head and second is tail, or probability of first is tail and second is head. Probability of A1 intersection A2 prime plus probability of A1 prime intersection A2 is equal to probability of A1 times probability of A2 prime plus probability of A1 prime times probability of A2 is equal to 1 over 2 times 1 over 2 plus 1 over 2 times 1 over 2 is equal to 1 over 4 plus 1 over 4 is equal to 1 over 2. Probability of HH is equal to probability of getting 2 heads is equal to probability of first is H and second is H is equal to probability of A1 intersection A2 in brackets is equal to 1 over 2 times 1 over 2 is equal to 1 over 4. That was how we arrived at the last column of figure 8.3. The distribution in figure 8.3 can also be represented graphically as figure 8.4 histogram of probability distribution for 2 coins. Probability of x against x, 1 over 2, 1 over 4, 0, 1, 2. We can as well express the probability distribution in a table as below. Sample space, tail, 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 head, head, tail, head, head, x, 0, 1, 2. Probability of x, 0.25, 0.50, 0.25. Finally, in statistical notations, we can write the above distribution as probability of x is equal to 0 in bracket is equal to 1 over 4, that is, getting 0 head. Probability of x is equal to 1 in bracket is equal to 1 over 2, that is, getting 1 head. Probability of x is equal to 2 in bracket is equal to 1 over 4, getting 2 head. Summary. Probability is a powerful tool in inference making at the face of uncertainty. It is defined as the ratio of the number of favorable outcomes of an event to the total number of equally likely sample space. An event is an outcome of an experiment. The probability of an event can only lie between 0 and 1. This is the end of study section 8. Thanks for listening.